Hello everyone, welcome to this tutorial on LangChain. If you have been following my blog on building the agent, you know that we have covered a lot of ground on using LangChain to build the pipelines. If you're not familiar with the LangChain already, I recommend you to go through my blog and try the collab notebooks with the blog series to familiarize yourself with the LangChain first. Now in this video, we are going to move from building the linear chains into stateful cyclic graphs. We are going to learn how to build agents that can remember, self-correct, and even ask for permissions for doing dangerous things. This is how the production-grade agentic chat surfaces are built, where they can reason and act, and at the same time can have an optional human in the loop. This tutorial is designed for Python developers who understand the basics of LLM, but they are new to the graph architecture. We will be working through two hands-on examples, a single agent and also a multi-agent team. So let's dive in. Now, before we look at the code, let's try to understand the why. In a standard LangChain, you build a pipeline. So data flows from A to the B and then to the C. It is efficient, but it is rigid. It is a fire and forget kind of a system. But think about how you solve a coding problem. You write code, you run it. If you get an error, you go back and fix it. That is a loop. Now to build a true agents that can fix their own mistakes or handle long-running tasks, you need an architecture that supports feedback cycles. We need a graph where the output of, let's say, the last step C, can feed back into the step A, the first step. This is exactly what the LangGraph provides. LangGraph is built on three pillars. First, there is a state. In LangChain, passing variables between different chains can get really messy. In LangGraph, we define a schema, a Python dictionary that can hold the entire state of the application. Every node receives this state and it can modify it and pass it on. Second, the nodes. These are just pure Python functions. One node might be your LLM deciding what to do, and another node might be your tool executing your search. Now, third are the edges. This is the wiring between the nodes. We have a normal edge. For example, this edge is a normal edge that goes from one step to the another step. And we have conditional edges also that uses logic to decide where to go next. So these are conditional edges. Now, if you notice the diagram, the tool node points back to the agent node, and this is a feedback cycle. Now let's start with the part 1 of our notebook. You can find the link for the part 1 of the notebook in the comments or in the attached blog. What we are going to do here is we are going to build a super agent node. So our scenario is very simple. We want an agent that can search for a user in the database and then delete them. Because deletion is a dangerous process, we cannot let the AI run on autopilot. We will add a human in the loop mechanism for confirming the deletion process. For this, we will use a straight graph for the logic, the memory saver to persist the conversation history before we jump for the confirmation from a human. Now you can open the part 1 of the notebook. So to get started, we will install the dependencies. You will need an OpenAI key to follow along these tutorials. If you do not have one, get one. You need to add your OpenAI key in the input provided. Now, once the environment setup is complete, we will move down to defining the state. So here is our state definition. It is actually a simple type dictionary. The key thing to notice here is the annotated list add messages. By default, if a node returns a value, it overwrites the state. But for a chat history, we want to append to the list. So add messages is a reducer function which is provided by LangGraph by default that handles this logic for us. It ensures that our agent remembers the entire conversation history. So I'm going to execute the step 1 for defining the state. Next, I'm going to define the two tools that we are going to use with our agent. One is a search user, which in production will use some sort of a DB query to find the actual user. But for the purpose of the demo, I have hard-coded a mocked out version which returns a user with a certain ID. Now I've also defined a delete user. In production, this will be actual implementation, but this will, for now, is returning a mock deletion. Now let's look at the main node of the agent, the agent node. The agent node is simple. It takes the state, passes the message history to the LLM, and returns the LLM response. The tool node is a pre-built node from the LangGraph. It automatically detects if the LLM requested a tool call and runs the Python function and returns the result. Okay, now going to the step 4 for defining the architecture of the graph, the loop. This is the most important part, wiring the graph. We add our nodes, then we decide the data flow. If you look at the should continue logic within this code, it is checking for the last message. If the LLM generated a tool call, it routes to the tool node. If it just generated the text, we go to the end of the node. And crucially, if you look at this particular code, which is doing the loop back, this is what is creating this self-correction loop. So after the tool runs, the output goes back to the agent so it can see the result and decide what to do next. Now let's add the safety. We compile the graph with interrupt before equal to tools. This tells the LangGraph if the graph decides to go to the tools node, freeze. It will save the state to the memory and stop the execution, waiting for us to confirm and then continue. Now let's run a scenario. We will send a request, a user message to the agent to find the user Raja and his ID and delete the record. If you watch the output, it plans the search. It hits the interrupt because it is calling a tool for doing the user search. Now for the second loop, we approve the deletion. So the state is now loaded from the snapshot where it was checkpointed. The agent remembers that the user has been already found so far. Now it is continuing with the deletion, and now once I approve, the agent should continue to execute the tools, and it will figure out that it needs to do a deletion call, and it will call the deletion tool. Now let's move to the part 2. The single agents are great, but for complex tasks, a single agent, which is a jack of all trades, that kind of a model fails. So we want specialists. We are going to build a supervisor architecture, which is usually, like, if you look at the production systems which are building agentic surface, most of them follow a supervisor architecture. Imagine a project manager, the supervisor, and the two workers, a researcher and a coder agent. The supervisor does not do the work. It just looks at the state. It just looks at the state and decide who should work next. Now in our team state, we will add certain fields, which is a next field. This string will hold the name of the next agent to run. In this case, it can be researcher or a coder. We will also add some flags to track the state of the execution, like if the data is ready or if the chart has been prepared, etc. and etc. You can use the agent state to store arbitrary state information, which can help in navigating the different turns while executing this multi-agent system. Now we create our workers using the standard LangChain agents, and this is your standard typical LangChain agent definition, but the supervisor is actually a special one. We use OpenAI function calling to force the supervisor to output a specific JSON structure so that it must choose one of the available workers or the finish. it acts as an intelligent router based on the conversation history, which keeps on getting accumulated. Okay, now let's wire it up and run it. The request is research the stock price for the Apple and then plot a chart for it. And this is our initial state that we do not have the data and the chart has not been prepared. This is our individual agents will actually work and update the state information and the results. Similarly to what we have done in the part 1, we are creating supervisor nodes, we are creating researcher node, we are creating coder node, and then we are wiring it all together using by adding the edges to define a workflow like this, where the supervisor is responsible for delegating the tasks either to the researcher or to the coder, and it also have access to the tool calling. Now I'm going to run the request. The supervisor sees that we have no data and it routes it to the researcher. The researcher finds the data and returns to the supervisor. The supervisor sees the data is ready and then it routes it to the coder, which is responsible for writing the Python script, and it returns the code back to the supervisor, and supervisor sees everything is done and routes to the finish. This is a cyclic graph where the supervisor acts as a central hub for maintaining the context across different specialities. In a production system, while the agent definition that you have written is streaming out the responses, you can stream these responses back to the front end or the client. And if you need to add a human in the loop for verification and approval, you can use a state check pointer to persist the state into a database, and whenever it is then resumed, you can preload the state information from the database. Now to wrap up, we saw that the LangChain gives you the control structures needed for the production AI. Whether it is a single agent that needs to ask for a permission or a swarm of agents working together, the graph architecture is the standard for the 2026 and the beyond. I encourage you to take the part 2 of the notebook and try adding a third agent, maybe a reviewer, to see how easily the graph can be extended. Thank you for watching. If you like the video, don't forget to like and subscribe. Thank you so much.